Hello and welcome back. This is going to be a very short episode. I thought I would revisit steel smelting, and the problems I'd always had with it before was because of inserter timings. The way to do moduled steel direct from ore is to have a bunch of iron plate smelters feeding into a bunch of steel plate smelters. But with beacons you have productivity. So let's zoom in. Right. So you have some productivity in the iron plates, and that adds you 20% to your output. That means one iron plate smelter can drive slightly more than one steel smelter, so 1/5 more. If you then have 5 of your iron plate smelters, you've got 5/5, which is enough to drive one additional steel smelter. So with 5 iron smelters, you can drive 6 steel smelters. You then speed beacon everything, and even after you've done that, because smelting takes forever, you can get away with inserters. In fact, I think we might be able to get away with slow inserters here. Yeah, we can. And we can definitely get away with slow inserters there. I've got a feeling this backs up if you do that. Let's take that away just to check. Yeah, so the number of plates in this machine is slowly climbing. It's because of the productivity bonus. So you need a fast there. But then I think you can use slows to feed the steel smelters. Let's check. Yeah, you can. So this is the only fast inserter you need in this build. Anyway, I'm not going to go back through it replacing all those. The logic of this build is you have a buffer chest, which is requesting ore. That then feeds into the steel smelter, the iron smelter, which turns it into iron plate. That gets put into this wooden chest. Let's pull that out for a second. Right. This is then capped to stop the whole system running away with itself. This then feeds into the steel smelter. That is then pulling plates, turning them into steel. That then puts it back into the same chest, the same buffer chest. So the steel plates going into the buffer chest, then bots pull here. It's a requested chest which requests from buffers. Okay, so that works. I've done a few videos of this on variations of this design, and until today it hasn't worked, but I think probably the devs have done a lot of work on the inserter logic, probably when they were fixing belts and things, and this now does work. So if we use max rate calculator, great little mod, Control N brings it up. You can then grab your build. Right, so max rate calculator, sorry, do that again, says that this should be producing 966 iron plates a minute, which are then consumed, so there's a net of 0 here, and 232 steel a minute. And when we, let's get rid of this, when we look at long-term production, you'll have to believe me on this because I'm not going to wait 10 minutes for a chart to plot. When you look at long-term production, this is within 1 or 2 single digits of being correct. So I'm seeing 964, 966 in that range of iron plates being produced. I'm seeing 230 to 232 steel plates. So unlike in previous releases of Factorio, when I was benchmarking this before, this build actually does work. So this is now suitable for on-site smelting, for example. If you want to turn an iron field directly into steel, this is now your unit for doing that. Okay, now loads of inserters, and they're all working all the time, and that's probably not a problem until you're building stupid big. The temptation when you're doing these is to slap down stack inserters everywhere. Now, the problem with doing stack inserters everywhere is that they usually, with slow builds like this, aren't moving a whole stack. So you can imagine, if we've got a slow inserter here, this slow inserter is moving not even as fast as a slow inserter can, and it's still keeping this machine fully fed. Right, this machine is not running out of ore. So we could slap down a stack inserter there, which would be trying to move 27 items at a time per swing, and it's completely overkill. However, this inserter here has to constantly check what the contents of the box are and what the contents of the machine are to see if it can swing or not. And that potentially is using up CPU cycles. So on this tiny build in this sandbox world, that does not matter. But for crazy big builds, these things start to add up. So I heard somebody on YouTube saying you can control the inserters using wires, and then there was a Reddit post, so I thought I would have a go. So this is the vanilla build. Okay, what we have here is essentially the same build, and with a bunch of logistics circuits going on. I have not optimized the wiring here. It was done for easy buildability, not for being neat or tidy or easy to configure. In the real world, obviously, you would wire this much more sensibly. But the intuition is we have 4 types of inserter. We have inserters inserting ore into the iron plate smelter. Then we have inserters taking the iron plates into the wooden box. Then we have the inserters taking the iron plates from the box into the steel smelter. And lastly, we have from the steel smelter into the buffer chest. So that's 4 categories of inserters. So they need 4 networks, the way I've wired it here. And each of those networks needs some logic. So the way I've done this is set up 4 separate red wire networks. And I've replaced all of my inserters with stack filter inserters, because if you click on one of these, one of the options here is to set the filter. You can set some other things as well, so you could choose to enable or disable it, you can choose to set its filter, and then independently of that you can choose to set the stack size. Okay, so what do? The idea is that the stack filter inserters normally have their filter set to nothing. So normally they aren't working. And as I understand it, the Factorio devs have special cased this so that when the filtering is set to nothing, the inserter isn't using any CPU cycles checking where it can pick up or where it can drop off. So that's great. What we then need to do is periodically turn on the filter. And I don't know if you can see it there, but this is flashing occasionally with the OR symbol. There we are. Okay. The way to do this is with a clock. Now, clocks are actually very simple to build in Factorio. I will build one for you right now. So we have a, can use pretty much any combinator here. Like we're going to use an arithmetic. So the input is going to be T for time, and we're going to output T plus 1. Okay, now if we were just to feed the output to the input, because each link of wire is calculated on a clock tick, if we now mouse over this, we need an output of T as well, sorry. So at each calculation, it's going to output T plus 1. And you probably can't see this, but there's a little ticker now, which is counting T, and T is getting bigger and bigger and bigger and bigger. The input signal is, say, 891, and the output signal is 892. That's great. So that just counts. And it counts once per UPS. So there's 60 UPS per second, ideally, per game second anyway. So 60 times a second, this is ticking. All right, that's great, but that just counts forever. So to make this a bit more useful, what you need is this little unit here, and I will grab this with a blueprint. There we are. Okay, so this is essentially the same thing. We have this combinator, which is inputting t and outputting t plus 1. That then goes into a decider combinator. When t is less than n, we output t at the input count. Okay, and what is n? N is what we're going to count to. So in this case, n is 90. So if we hover over this, this now counts up to 90 and then resets back to 1. And the intuition is n is our maximum number, like a loop limit in a for loop. T is like our loop counter. So t is going to count 1, 2, 3, 4, 5, 6, 7 until it hits n. At the point where it hits n, instead of outputting t, we're going to output 0. That means that the input here for t is 0, so it's going to output 1. This resets the loop. So if we take wires out of the top, we have a counter from 1 to n, and if we take wires out the bottom, we have a counter from 0 to n minus 1. Depending on if you like doing things the C++ way or the R way. Okay, then what we can do is take the wire out from here and put it through one last combinator. So this is a decider combinator. It takes t. If t is less than or equal to 1, it outputs iron ore. Then we take that by the red wire and feed it into our filter inserter. And now once every 90 game ticks, so every second and a half of gameplay, this flashes with the iron ore, and at that point this filter inserter has the option to insert iron ore into this machine. Right? And you can see it does it. Now I haven't fine-tuned this, so n of 90, it can probably be a bigger number than that, because you see sometimes it flashes and the inserter chooses not to move, presumably because there's nowhere to move it to. But already you can see it's only very rarely, so every 1.5 seconds of gameplay, that inserter comes alive. All the rest of the time, that inserter is inactive. So then we do the same thing here. We have a timer for taking the ore out of this machine, so you can see it's producing about 9 plates before this tries to take the ore out. Okay, and that's done with an n of 90. Okay, so we could probably up that, right? So a stack inserter can move 27 items at once. So we could bump that delay up until there were 27 items to move. However, that doesn't entirely work in this case, because we are taking from a single box and putting into 2 steel smelters. These ones, I had to override the stack size so that they only took half a stack. That gives this box a fighting chance of feeding both to the left and to the right. The other thing I needed to do was set it so that these were active on a clock which was linked in time to this one. So there's actually a slight delay because I take a wire out from here and then it gets fed into this little logic here. So if I've understood how the wiring works, that's introduced another 2 clock ticks of delay. But that means that by the time that's put it in there, these have then come active. And the other thing I needed to do was set the thing here so t is less than 10. That gives it 10 clock ticks within which it can move the material. That allows both these arms to swing, and if there's any material left over from one of them, because it's filled up its smelter, the other one can swing as well to grab. So this actually works very well. This setup here with all these combinators keeps this within about 4% of peak performance. There's a slight problem with these end two smelters occasionally running out of input, because what I should be doing is swinging this inserter more frequently or with a higher stack size than this inserter to compensate for this being fed from 2 and this being fed from 1. I haven't bothered to do that. That's like literally last 4% tuning in this case. But the UPS of this would be very much lower than the UPS of the one above because we're doing so fewer inserts. If I was doing this in real life, I would consolidate all these bits of logic down into a single area. I'm using N as the signal for the counters everywhere here. I would have, in this case, 3 or 4 different signals as my limits, put them all on a single constant combinator so that I can set them all centrally. I would also consider, at the moment, I'm using filtering to set the to decide whether the arms can swing or not. The problem with that was I had to segregate the network into 4 networks, which is annoying. What I could have done instead is wire the whole thing into a single wired network. And if we look at one of these things, when it's wired, there's an enable disable. And if you enable it, then you can set a condition for when it should enable. So that would allow me on the single, I could set 4 different conditions for the 4 different types of arms, or, well, probably actually 5 conditions, because these single arms are special cases. I would fire 5 different signals down the network on 5 timers, and that would let me centrally control everything over the one wired network by turning the arms on and off rather than by setting their filters. That would allow me to use bog standard stack inserters, which would make the build cheaper, of course. Anyway, I thought I'd show this. It's the first time I've tried to use this kind of wiring to shave off the last few % of performance. The other thing you can see here is these bots are working all the time. These bots are obviously only working in bursts because the ore is only being fed in bursts. So there's a lot less traffic on the logistics bot network as well. Right, well, thank you very much. Hope you enjoyed this. If you did, like and subscribe. I think that's the form of words people use. And I did have a brief go at doing my base in a book and realised that I totally suck at the early game. So I burnt through my first 4 hours just getting to red belt and laying down blueprints, and so there just wasn't any possibility of me getting done within 15 hours. And also I'd kind of made some bad errors with my starter base, boxed me into all sorts of corners. So what I've been doing is playing in Sandbox, running through various starting scenarios. I think I have a starter base blueprint now that I'm fairly happy with. So I'm going to have a playthrough getting started with that, see if it goes anywhere. I'll record it, and if it isn't an utter embarrassment, I'll put it up. In the meantime, enjoy Factorio, and I'll be back soon.